Hello, everyone. Hello. It's good to be back after a little break for the summer to this Surface Ventures workshop on fretting and extreme pressure. Very interesting one for me. So we've got a little bit of chat activity. It'd be good to say if you could all say hello, tell us where you're joining from. That would be great. So before I fully launch into the part, okay, great, Coventry, Australia, Estonia, brilliant. So before I launch into the talking about the fundamentals of fretting, I would like to welcome the team from Optimol on stage, please, to introduce themselves, as they will be talking a little later in this webinar. So they should be on stage shortly. So just to cover, okay, no, brilliant. We'll go ahead and. Hello, everyone. Please go ahead and introduce yourselves.
Hello, everybody. I'm Gregor, the Managing Director of Optimol Instruments, and we are very happy today to support this event and to give you a live demonstration later on. And we will be happy to answer your question about the experimental setup and user friendliness of our devices.
Hello, everybody. My name is Felix. I am the working student by Optimol Instruments, and I will show you today how easy the SRV is to use and what for tribology question you can answer it.
Hello, my name is Laura. I'm the ETS product manager from Optimol Instruments. This is an easy screener for tribology, and I'm happy to be here with you.
Okay, fantastic. Thank you, everyone. Right, so I'll if I could ask you to leave stage for now, please. I'll go ahead and start. Okay, let's begin. Well, in momentarily before we begin, I would got a few poll questions. So one of these, just I'm curious how familiar the audience is already with fretting. Somewhat experienced, and some very experienced, some not at all. Okay. So as I was about to cover before our introductions there, so we will be focusing first on covering the theoretical and sort of fundamental elements of fretting wear and extreme pressure, as I have done with previous workshops. I'll try and answer questions as I go. If they're a little longer, I will mark those and then try and answer those in the Q&A session immediately following my section of the workshop. After that, I will hand over to Gregor, who will talk through the setup of the SRV platform. We will then have the live demo, and we will have a second Q&A focused primarily on the instrumentation. However, if you do have other questions on the fundamentals of fretting wear, please go ahead and ask them. We will try and answer those as best as possible. Okay, 31 attendees in. Excellent. So, quick overview. So we're going to be covering, as I said, the fundamentals. We'll also cover some of the analytical techniques that have been applied to fretting, and also to explore some of the methods that we can use to combat fretting in these extreme pressure environments. So to cover a little bit of important background material, some of this was covered in previous workshops, so I'm sure some of you might be familiar with this, generally from your studies and from your work, but also from what I've spoken about in previous workshops. So important things that we need to sort of quickly cover: surface structure, Hertzian contact mechanics, and synergistic wear. Fretting is complex, and there are many factors that affect fretting wear. Okay, so surface structure. So first of all, let's review this sort of standard structure of a surface. We have our surface texture or roughness, and we have multiple layers. So physisorbed and chemisorbed layers, chemically reacted layer up to 10 to 100 nanometers, then our amorphous bilby layer, and then the various deformed layers depending on the mechanical loading of this material. Fretting is a dynamic process, and this can change the structure of material, specifically tribologically transformed structure, which has been covered in literature quite extensively, and I will be talking a bit about this later. So one thing to keep in mind is this is our sort of standard kind of model of a metal surface, but fretting does change this. Of course, where more should we say traditional types of wear, like sliding wear, pin on disc, of course that changes the material as well, but it tends to be less responsive to the actual wear process. Fretting itself, there's a lot of feedback and interconnected elements in that. And another thing as well, since I bring up surface texture, is that this can affect the fretting response. Fretting is quite sensitive to surface roughness. And now coming on to Hertzian contact pressure, when we are looking at modeling fretting tests, performing fretting tests to model fretting that happens out in the field, one of the things that we need to be aware of is what is the nominal Hertzian contact pressure that we're dealing with, what is the geometry of this. So typically we can, one of the easiest things to look at is sphere on flat plate. Of course, with this we have a specific contact radius, a thing that when you are looking at setting up a fretting test, you should always calculate this. What is your sort of nominal radius of contact? Of course, this is going to change during the test, but it's something you should be aware of. And one of the most important things is what is your maximum Hertzian contact pressure relative to your contact radius and the type of geometry that you're using, because this really sets up how well your test is going to mimic what you're actually looking at, modeling. Okay, and then by extreme pressure, what do we mean? So for reference, I have this paper down here, single cam tribometer paper, excuse me. And for that, the contact pressure of 610 megapascals was used, and this was used to replicate a valve train in an engine. But for extreme pressure, typically this is much, over 1 gigapascal, if not much greater. This is where the contact stress exceeds the yield strength of the material, or can. And of course, with this, we will get a higher Hertzian contact radius as the load increases. Higher contact pressures, we can increase the contact heating. Once again, that's going to drive that dynamic change in the structure. And this is where lubricant optimization for this, if it is a situation in which you are inserting a lubricant, becomes much, much more important, because we need to think about what's the viscosity of this. Is the lubricant being squeezed out? So these are all things to consider. So what is fretting? In short, high frequency oscillatory wear, typically with short amplitudes, where the relative motion is generally no more than 150 microns. That figure was, I believe, taken from one of Waterhouse's papers. Excellent papers to look up if you want to look at some very fundamental literature for fretting. For any greases and materials with load carrying capacity, we need to ensure that the surfaces are protected. If the pressure is high, if the relative movement is much higher, this creates a lot more wear particulates, wear debris, which again I'll talk about in detail a little more later. Whereas if this is smaller, we're then talking about a more fatigue-driven process. So all important things to consider. Having low friction and low wear rates improve the service life of materials in this. Typically stops the generation of some of these, a lot of particulates, and then the higher the load bearing within an acceptable efficiency range can really help in these situations. So what I'd like to quickly do as well, so I've asked how familiar you are with fretting. I'd also like to just quickly take an aside to share a question on what describes your current position. So just asking about academia, industry. Okay, thank you, industry professional. It's good to see so many industry professionals here as well. So nice, a little bit different from our previous workshops. Thank you very much for answering the question. If anyone else hasn't answered the first poll question, could you please do that as well? I'll be very appreciative of that. Thank you. Okay, so let's so getting back into this, the morphology of fretting wear. What do one of these wear scars look like? So what we have here is a fairly typical fretting wear scar. The first of which is a little bit more wear driven, whereas the second, the load is not quite so severe, and we have more of a fretting corrosion, fretting essentially oxidation type of scenario. So in the first one, or the one on the left, sorry, we have false Brunelling. So what appears to be a false physical deformation of the surface. And then beneath that, we can see the actual diagram of what's going on here. We have the central, seemingly undamaged area where the actual contact was maintained. This is the section of the wear scar that is unrevealed during fretting. The outer area is defined by pure slip, and or pure sliding, apologies. And then the more central area, partial slip. So we have essentially a stick section right in the middle. This will move, so then you get slip on either side of that, and then sliding around the outside. Whereas with our fretting corrosion, we have our unrevealed section of that wear scar in the middle, and then our essentially two oxidized portions of this either side. Okay, so a quick audience question for those of you who were, perhaps for those of you who were in previous workshops. Fretting wear is commonly known as a synergistic wear mechanism. There's more than essentially one thing going on, as there is with all types of wear, of course. But you get some. I like to just sort of field a few responses in the chat for what fundamental wear mechanisms you think synergize in order to create fretting wear. So oxidation, yes, excellent. The more oxidation and abrasion. Yep. Abrasion, sliding wear, yes, we can look at sliding wear if we have higher amplitude fretting. Abrasion by oxidized particles, yes. Yes, excellent. All good answers. Thank you. Adhesion as well is another one. Yes, there we go. That's it. Yes. So adhesion. So depending on the contact conditions and the exact and the ambient conditions surrounding that, we can get adhesion. Cold welding of absolutely. This can really. Thanks, Felix. This can really really drive the wear in those depending on the ambient conditions of this. And that can be some of the things that we need to optimize for grease a little later. And now coming on to this, so all correct answers. Thank you very much. So surface energy is absolutely something that we need to think about. Well, in terms of energy distribution on the surface. Thank you, Marlon. So I have a little bit of talk about that. What's that? My understanding is that max amplitude for tests to be defined as it depends on the size of the contact, should be less than the size of the contact. Yes. Yes, absolutely. So there are different ways. The different fretting regimes are defined. There are multiple ways to define this, but generally, yeah, we need to think about what the amplitude is relative to the size of the contact. So I'll talk about that a little later. Thank you for that comment. So, where do we think fretting occurs? In what industrial scenarios would we see fretting in? Where do you think? And this can occur in a lot of different places, but there's a few sort of general ones. Rotating machinery, absolutely. So if we think again back to that, so oscillatory motion, vibratory motion, windmills, excellent one. Yeah, wind. Yes, wind turbines, car transport. Yeah, it's a really good one. A lot of car components during transport. Bearings, excellent one. Again, I did give that one away a little bit with my gas turbine blade. Yeah, disjoint. Yes, absolutely. All great answers. Thank you very much. So moving on. Yep. So wind turbine bearings, as we said, industrial gears, drivetrain components of electric vehicles, hybrid specifically, although normal, are sort of full electrics as well. Engine idling can induce some of this oscillatory motion, vibratory oscillatory motion. Electrical connectors. That's that question. Thank you for your question. So that one, I will cover that one in the Q&A section. If they're quick little questions, I'll try and get them as I go. Otherwise, I will mark them and answer those in the Q&A section. Thank you. Electrical connectors, another thing that can cause you have quite extreme failures. Biomedical implants, as we see here. So titanium and stainless steel, and within ropes and cables, so big cable bunches, when you have changing loading, essentially as that you can get torsional fretting between the ropes and cables, which is one that's not mentioned quite so often, but there's a few papers out there that are quite interesting, which I'd recommend you take a look at. So why is this a challenge? For one, it is very difficult, and a lot of the equipment that we need to use for this is very specialized, and it needs to be quite specific to this because we have high frequency, very low amplitudes. If we're looking to mimic a specific fretting condition, so depending on the actual amplitudes for these small amplitudes and for the high frequencies, fine feedback control is very important. High load carrying capacity is required as well for the actual equipment, and you need to ensure that your equipment is very sturdy in order to be able to mimic the conditions that you're trying to test properly. And as we sort of mentioned in the earlier slide, for optimal endurance in fretting conditions, we want low friction, because essentially this means there is less wear energy imparted to the surface, and of course low wear rates, because we want to generate the smallest amount of wear particles possible. So I will come on to the type of techniques that we can use for this a little bit later. There's quite a few. And then one of the things we want to do is we want to improve the efficiency of the system and try and enhance product durability and endurance. So fretting modes and mechanisms. So I sort of alluded to the fact that there are different types of movement associated with fretting wear. Most often we think about tangential mode because this is one of the easiest things that we can instrument, that we can put in a machine and test, because essentially we're putting in this example a ball on a surface and moving it back and forth with varying amplitude. Of course, there are different types. There is the torsional fretting that I talked about for ropes and cables. We can think of this as rotation between a ball and a surface. There's also rotational and radial. So multiple modes of movement there. Typically, if you look in literature, a lot of the for testing materials, again, we try and simplify, as with any tribal test, we try and simplify the contact conditions as much as possible. So while still trying to mimic the contact conditions of what you're trying to test. So ball on flat tends to be, or sphere on flat tends to be one of the easiest things that we can look at, as well as cylinder on cylinder is relatively easy to set up, or cylinder on flat as well, depending on the exact type of contact conditions. So that's just a thing to bear in mind as we go on with this. And now coming into now we know what our movement is. What does this look like? We have a little model sort of frictional loop, or what we call a fretting log, when we can extend this. So we have our two-dimensional version of this with our frictional force and our tangential relative displacement. We'd of course extend this into 3 dimensions by adding a time axis. So we'll take a look at some of these, and I have some example data of this from some of my work a little later. So you can see how this changes. It can tell us a lot about the conditions of your fretting process. One of the things you want to do is make sure that whatever type of equipment you're using, you're able to measure this as you go. It can tell you a lot. So this hysteresis loops, this closed loop, essentially we're expending energy into the fretting contact. So it's defined by our friction coefficient. So essentially that gives us the height of our log, and the contact stiffness, which gives us our sort of how steep it is. The higher the contact stiffness, the sort of steeper it is, the steeper our sort of loop is, the lower the contact stiffness typically. Then this can change. So our contact stiffness we normally measure by the gradient, just at our sort of change in displacement. So you can either do this at the far right or the far left, and then you can see your sort of micro slip as it changes direction. We have full sliding, so right at the top. So we can, if we look at the values of friction at the very top and bottom, we can then use that and find what our root mean square friction is for these, and that can give us our friction during sliding. So that's for the hysteresis loop. The fretting process itself is of course defined by whatever our friction force is and the relative displacement. And as I said already, very important to monitor the dynamic changes in the fretting process as we go through. Because this is very important to tell us about how the system changes, how the dynamics of the system are changing the contact, and so on. But we'll cover this a little later. So how do these loops change with fretting regime? Again, feel free to put any comments in, but just I'm aware of time, and I want to keep moving. So we have different fretting regimes, as I talked about earlier, which are defined by essentially what the actual displacement is and the friction. And there are 3 different shapes that we typically associate. So we have our partial slip regime, effectively with essentially not a full hysteresis loop. There's very little area inside that. It can change a little bit, but typically we have so this is the lowest amplitude fretting generally. We can then get mixed regime, so where we're moving between our gross slip, which is the highest amplitude of this, typically with the highest amount of friction, and partial slip, so transformations between these processes. So in this is probably where we're getting the most interaction between the different elements. So friction could increase dramatically, so we drive the displacement down. But if wear particles are then moved out of the newly forming wear scar, the displacement could increase. There's a lot of dynamic things happening, a lot of interactions happening. I mean, this is just an example, not necessarily what happens in all cases, but something to think about. So very important to define what regime it is you're working in. What are you trying to model here? So how do we determine the criteria for each regime? There's quite a few of these, and I'm not going to cover all of this in rigorous detail, because again, the replay for this will be available. It will be sent to all of you, and it will also be available on our website later. I've put the references for all of these where I've grabbed these transition criteria from. So I would recommend, if you are particularly interested in these things, to take a look at those papers. But we got quite a few. So Minlin's slip ratio, which was the earliest of these. So basically, giving us what would be the transition for partial slip. We can also think about a transition in terms of coefficient of friction. So once our static coefficient of friction is overcome, we can look at it transitioning from a more stick-driven process to a more sliding-driven process. We have energy ratio. So between essentially lower than or equal to 0.2, we're in partial slip. Higher than that, we are in gross slip. Slip ratio used by Fouvery, so 0.26, lower than partial slip, higher than 0.26 in gross slip, and then we have slip index as well. So each of these papers will tell you all of the parameters for this, but without extending too long and without making this just talking about maths. That's what there is. I would recommend that you do a little bit of further reading. So in addition to our fretting logs, we have fretting maps, two of which. So the running condition fretting map, so lower displacement amplitude with whatever normal force it is, we have partial slip. Increasing the displacement amplitude, we have our mixed fretting regime. And then the highest displacement amplitude, gross slip. One thing, of course, to mention is that should the displacement amplitude go so high as to entirely reveal part of the wear scar during any part of our process here, that transitions into full sliding. We're no longer in fretting because we've essentially lost some of the fatigue component in that. So if we were to increase that displacement amplitude, we could then add another line and say, okay, this is into full sliding. And then we have our material response, which I've alluded to a little earlier. So with our partial slip, because there is such little movement, this is fatigue driven. So we can think of this in terms of low cycle, high cycle fatigue. So low cycle fatigue, typically higher load and much shorter cycle time, of course. High cycle fatigue, very crack driven, lower loads, much higher cycles in terms of the hundreds of thousands versus just maybe thousands for the other fatigue mode. Mixed fretting is where we're beginning to generate wear particles. And then, but of course, there is still this fatigue mode there. And then gross slip, very much driven by debris formation. This is where our oxidation comes in. If you have a contact in which oxygen can get to, you will oxidize your wear debris, creating hard particles, third body wear, increasing the wear during your fretting process. So something to be aware of. So wear coefficient in fretting. So this is what we have here on the right is a graph taken from a Pearson and Shipway paper, relatively recent, 2015, where they were talking about is wear coefficient depending upon slip amplitude. As this is something that has been talked about a reasonable amount in different fretting literature, referring back to Vingsbo and Soderberg, who ordered that wear coefficient is a function of displacement amplitude. However, there's been some misinterpretation to say that this is then slip amplitude. Obviously, these are different. Displacement being the total movement, slip being what is our sort of more central section, the amplitude for that more central section, not defined by the full sliding part, should you have that for a more gross slip. So Pearson and Shipway concluded that the wear coefficient is independent of slip amplitude, but of course this displacement amplitude still holds correct. So our stick much lower wear. As we increase that displacement amplitude, we're increasing the amount of wear, increasing most over our displacement during gross slip and then into reciprocating sliding. So one of the things that is important with this, again, to highlight, whatever piece of equipment you're using, you want to make sure that it is able to monitor everything during the process, or as much as is feasible to instrument. So I talked a little bit about third bodies in fretting. So gross slip, our sort of highest amplitude fretting regime, is characterized by debris formation. So this is where these sort of synergies really come into effect. Abrasion of the surface, adhesion between the surfaces, and plastic deformation between them is going to generate wear debris. We can get strain hardening right on the contact points, micro cracks forming around them, and this can tribologically transform the structure, so generate wear debris. These will fragment, create lots of particles. You will of course have oxidation as well. Oxides of a material are harder than the material itself. This drives increased wear during the process. And one interesting thing with tribologically transformed structure, there's been quite a few papers on this. Tomasz Lichwicz on nanoindentation of fretting-induced surface layers. This is very good paper. I would recommend that you take a look at that. It's a performing fretting wear, but then nanoindenting and essentially creating a map of how the hardness and reduced modulus change in the fretting scar relative to the area around it. So there's been quite a bit discussed in literature surrounding, of course this transforms, but how does it transform? One of the easiest ways is to actually measure it. The mechanical properties do change over longer periods of time. You will get oxides forming. These will typically be thrown out of the wear scar, and you will instead get this softer region, and this region where it is not as stiff after fretting. And I'd said earlier, roughness in fretting contact. Another great paper here by Kubiak looking at roughness and how this affects the wear rate, as well as coefficient of friction. So with our initial surface, this is of course initial surface roughness. Again, tribologically transformed structure, the roughness will change throughout this. As roughness increases, coefficient of friction reduces. Conversely, as roughness increases, wear increases. So you can essentially think of this like in terms of our ideal surface, our asperity contact with coefficient of friction, a rougher surface, you are getting fewer points of asperity contact, whereas with higher initial surface roughness, you're essentially getting more focal points for the stress of your fretting wear that's going to create more wear debris. Essentially, the tops of these asperities are going to break off, driving wear. Excuse me. And another thing I want to talk about, we typically associate this with the sort of micron scale, but of course, this sort of idea of a vibratory or oscillatory contact, we can scale this down as well to nanofretting, essentially filling in the measurement gap between AFM at the very low scale to our sort of micro fretting and sliding there. So we can think of this as sitting right in the middle. Typically with this, we look at H over E ratio, so hardness to elastic modulus ratio, that would normally drive and control a lot of the wear response for these small scale wear scenarios. However, that isn't quite the case here. Just mark that as another question. Thank you. Useful to correlate with, yeah, so, sorry. So one of the things with this paper by Ben Beek is to using multiple techniques. This is when we get to the nanoscale, it is extremely difficult to no one technique can control everything. It can monitor everything. So especially on this small scale, what you want to do is you want to use as many techniques as possible that give you multiple pieces of information about your material, because this becomes more of a material characterization issue. And this can look at, and with this we can look at wear depth, we can look at friction, we can look at then bring in nano scratch as well, then to look at contributions of interfacial friction and plowing friction, because we're now looking at more fundamentals of interaction. And then with we're load dependent. Yes, load dependent with low amplitude nano fretting. There's a lot of load dependence. The higher the amplitude, we get more production of third body wear particles. And now coming on to combating fretting. So one of the easiest things to, or one of the best things to do when you have fretting wear, of course, there are multiple other techniques, as you can see on this slide, but the first thing you should always try and do is, can this design be changed? Can I try and reduce the contact between these surfaces? Can I change the design in order to remove this oscillatory contact? Because after this, the techniques become a little bit more complex. The first of which isn't too bad to do, but depending on the complexity of your component, this might not be feasible. Introducing compressive residual stresses, because this combats cracking, especially if you have something with a lower amplitude fretting where you have partial slip, mixed slip. So if you add compressive residual stresses, shot peening is a good way to do this. Quite extreme forms of hardening. I'll come on to that DLC question in just a second. Thank you. Application of hard coatings. So this will, of course, increase the wear resistance. These are harder coatings, typically going to be harder coatings than whatever the counterface is to that. And then, of course, these coatings themselves can have compressive residual stresses, which can combat cracking for small amplitudes. So what type of DLC would be more suitable? So for these, typically this is in this up to micron scale regime where mechanical properties are going to determine your fretting response. A higher H over E ratio is better for this, but you don't want to go to a full, okay, well, let's remove the hydrogenation from this and we'll go to tetrahedral amorphous carbon or amorphous carbon. That is going to give you a very poor response because the friction is very high with that. So you're going to get a lot of energy expended into the fretting contact. So hydrogenated amorphous carbon would probably be the type of DLC that would perform best. It has a high rate H over E ratio. It is lubricious. It has you will form a tribal layer in that it will graphitize. So yes, you are going to form wear particles, but they're going to be helpful in your contact, and it has a lower coefficient of friction than some of the harder DLCs. Application of a lubricant or grease. I'll go into this a little bit more later. Sorry, I'll just mark that question for the Q&A. Thank you, Yuri. Yes, so this is one of the things you need to think about, the exact type of lubricant or grease that you use. We can think of a dissipated energy approach in order to, once again, supplement our monitoring techniques, and then solid lubricants. So adding graphite to a contact, chameleon coatings, somewhat straddling the line between coating, a coating or a solid lubricant, coatings that can dynamically adapt to their conditions. Andrew Vavoden's papers are excellent on this, and I would recommend that you take a look at those on chameleon coatings. There hasn't been too much literature on those for fretting wear, but for a dynamic fretting process, having a coating that can dynamically change as required is great. So dissipated energy. So this is a technique used in a lot of Fuvri's papers. So we have our little diagram up in the top left there. If we think of our fretting surface, so we have our sort of Hertzian contact that is moving. We have our unexposed surface in the middle. This is our more fatigue-driven part. Our sliding ratio. So essentially, we can think of this in terms of there's an amount of energy that is expended within this contact. The longer the fretting wear goes on, the more energy there is there. The more tangential force you apply, the more energy you're going to have as well. If you then increase the sliding ratio, drive it into full-scale sliding, you're then going to have energy distributed across a larger area. But we can think about this then in terms of, so the amount of dissipated energy density, so the amount of area for your fretting contact, the amount of energy that you have. So if you integrate your dissipated energy all along your fretting logs, and then think about that in terms of how much, well, you think about this in terms of your ideal area. What is your dissipated energy density? You can perform multiple tests in order to find what your coating lifetime is. And this produces this wonderful little graph here on the left. We can rearrange this. So in terms of fretting lifetime, number of cycles, and dissipated energy. And then we can also think about, for the amount of dissipated energy on the surface, what was our wear depth? So parameterizing this, thinking about this in terms of the maximum number of, what can we measure, what things can we correlate. And then another paper by Ito et al. So showed that we have a quite good correlation between acoustic emission and dissipated energy in fretting. So another technique that we can use to measure this. So moving on, as I said, lubricants for fretting. Oil lubrication is very sensitive to normal contact pressure, and viscosity is extremely important because you don't want your lubricant to just be squeezed out of your fretting contact if your pressure is too high. However, if you can optimize this properly, you can get a quite good reduction in your friction coefficient, as we see in the diagram at the top. So you will get an increase in your friction at first. All of these have to stabilize first, and then the friction will drop. Lubricant is also great because it can inhibit oxygen access to this, which can also reduce the amount of oxygenated debris. For gross slip, grease lubrication is most important. When we have different displacements here, we can see how the coefficient of friction changes for a different number of cycles, and low friction additives, things like MODTC, can be quite good. Other methods protect against extreme pressure. Arc oxidation, so making the surface harder, laser alloying, and there's been a little bit of work to show that some nanoparticle suspensions can be quite good, specifically against some extreme pressure scenarios. So I want to talk a little bit about, traditionally when we talk about extreme pressure, one of the ways that we look at this in terms of materials is a 4-ball test. This is not fretting wear related, but or not the typical thing that you would use in relation to fretting wear. This is a materials characterization technique. However, I feel since we're talking about extreme pressure, we should also mention this as an applicable test technique. So generally you will have 3 balls on the bottom, 1 on top. The load is applied to this top ball, and rotation applied to it. For an extreme pressure failure test, the load is continually increased throughout the test. And this can help tell you when, once the lubricant is squeezed out, then you know the pressure at which it will no longer function. Once you have surface-to-surface contact, you can get cold welding, which of course, as Felix mentioned earlier, you can get this in fretting as well. And with a well-built fretting machine, you can instrument way more things and measure way more things than you can in a 4-ball test, just because the geometry is much more difficult to actually measure this. I mean, we can tell with a load, and then our sort of catastrophic failure condition is essentially when we have sharp changes in the friction signal, whereas with a good piece of fretting equipment, we can keep the test going. We can say, okay, the friction's increased, what's happening in the contact, and so on. So, and of course, this can also operate in a wear test mode. So we just keep the load fixed. Lower balls are fixed, the upper ball is rotated, and we can measure the load, temperature. We measure friction between these, keep the load, temperature, and speed the same. I want to review quick little bit. So looking at time, I'll just move on quickly. So some fretting conditions here. So this is in gross slip, sliding ratio of 0.56. Typical lab conditions here. 10 millimeter diameter, 52-100 steel ball. These are against various different types of DLCs. With a stainless steel substrate, we have our coating A, which is our amorphous hydrogenated. B is silicon doped. C is tungsten doped. So we can see here quite nicely as they separate by H/E ratio, like I talked about earlier. So our highest H/E ratio, coating A, lowest, then B, then C, and then uncoated right at the top, with extremely high coefficient of friction, as you would expect from an uncoated sample. And you can note the change in the morphology of these. Tool steel, once again, very similar. A little bit more dynamic changes with this throughout the cycles. And then we can look at our fretting logs and our sliding ratio. So also these with different types of lubricant. What we can see uncoated is that we have our instability right at the beginning. This then extends into our set gross slip as the machine's feedback loop kicks in and is able to keep this within the measurement parameters. We see that again with coating A, this instability. However, the friction force is far smaller. Our energy expended is far smaller, and then far smaller once again with base oil. So that's we'll have some questions in a minute, but one of the things I want to say is we have our next Surface Ventures event coming up on the 30th of September with Dr. Tom Reddyhoff from Imperial College London, talking about soft tribology experiments. I'll release the link to our website as well as one of these little featured actions. So please, I'll release that a little later, so you'll be able to go to our website, see a little bit more about us, but please feel free to register for that. And now I'll quickly go through the questions that we've got and then move on to bring Gregor on stage momentarily. Okay, so the first one, can conformal contact be evaluated using non-conformal Hertzian contact? How accurate will it be? So conformity in contact, you can, you're essentially thinking about like how well do these surfaces conform to each other. If you have say a cylinder, we have a cylinder within essentially a half pipe shape. We can think of this as a relatively conformal contact. You can do that. You could do sphere on sphere. These two surfaces don't conform together quite well, but there will still be a point contact between them. So yeah, you can do that. One thing to say, of course, is that Hertzian contact is this presumes elastic deformation and is quite useful to give us our initial starting conditions. So as the process changes, the Hertzian contact is no longer valid. So one thing to think about there. Another question here. Could you remind us of this research focused on incubation stage during fretting? So on the, I think if there are any papers that come to mind. So unfortunately, I can't think of anything. Nothing is popping to mind immediately talking about this this incubation stage. I'm quite sure it's. I'm sure there are papers out there, and I think probably quite a lot. I think a lot of the papers that I've referenced throughout this, if you want to go back and watch the replay, do talk about this incubation stage. So I hope that's helpful. Sorry, I can't think of anything off the top of my head right now. And then another one, can use of dissimilar materials on two contact surfaces reduce the risk of fretting? Yes. So that is one of those. Typically, optimization against fretting generally happens way later in design. So a lot of the times that's why we say change the design if possible as a first step, because then it's applying coatings, hardening materials, changing materials. So you're going to look at, okay, which of these two surfaces, one, can we modify, and two, is able to be easily modified as something that's like the coated surface, for example, one that you want, that ideally you would want to replace far more rarely than whatever your counterface is. So of course, be aware that the harder surface is going to be the one that's going to receive far less wear. as compared to the other surface that is softer. Think about our normal laws of tribology. The softer surface is going to be the one that wears. So yeah, you can kind of optimize these between the two, but of course it's once again about whatever the friction force is and whatever the displacement is. If you can reduce the amount of energy expended in a fretting contact by use of a specific material, great. You're going to get less wear, because the more energy you put in, the more wear you get out. Okay, so thank you everyone for clicking on that featured action. That link is also on our website, which I'll bring up a little later. So I'll remove that for now. And I would like to invite Gregor on stage so that he can talk to us a little bit about Optimol and about the SRV platform.
Yes, thank you, Sam. The last question by Yuri was very interesting, and your answer also, because this is exactly where tribology testing jumps into this problem. Because with the tribo tester, you can, on the one hand side, easily evaluate material combinations before you start the design process, or while you are within the design process. You can simply vary the materials in the tribo test and evaluate the fretting performance of the fretting compatibility of the materials. And on the other hand side, you can also test not only ball on disc geometries, for example, but also conformal contacts like area contacts against flat. And this helps you to answer many of those questions which you rose in the Q&A session. Just one step back before we start then with the presentation or with the demonstration. Optimol Instruments has a very long history in industry. So in the very beginning, we were part of the Optimol lubricants factory in Munich. So our roots are in the lubrication industry. And already in the 1960s, which means over 50 years ago, we started at Optimol to invent own tribo testing equipment, because we observed that it's very expensive in time and in money to produce results only in the field. So, and this is our philosophy, which started already in the 60s. We have to simplify the problem to reduce it to the real effects which occur in the field, bring it to a simple lab scale tester, find solutions and results, and then scale the problem back to the real field. And this is exactly what we are doing all the time. So Sam, can we switch to the next slide? I can also control it.
Yes.
And you see it here. So since 65, we are steadily producing and inventing and improving the SRV tribometer, because this is exactly what we are doing. When I talked about the downscaling and upscaling of the problem, you can simplify the problem, bring it to the tribo tester, find your answers and solutions, and scale them up back to the real life. And this is why one of the reasons why the industry standardization communities worldwide accepted the SRV as a fundamental tribo tester. We have more than 20 standard methods worldwide, many industry specifications. One of those standard methods is, for example, the ASTM D7594, which focuses exactly on fretting wear in grease lubricated systems, but it can also be used for non-lubricated systems and coatings and other material combinations. You can always reference to this standard method. And Just to show you shortly the test principle in the SRV. So you have a loading device which applies a normal force from the top. And on the left-hand side of the test chamber, you will see later in the video demonstration, we have a linear actuator, which is free from mechanical wear. It's electromagnetically driven, so you don't have wear within the actuator, neither friction nor vibrations. So you have a very smooth and straightforward actuator. And the upper specimen is moved by this actuator, and the lower specimen is kept static. And at the lower specimen, we record the friction force by piezoelectrosensors, which, that have the big benefit that they have a huge dynamic range. So you can detect very small frictional forces up to very high frictional forces. And they are very quick in reaction, so we can very highly resolve the signals down to 2 microseconds. That would mean if you run with 50 hertz, you can resolve about 10,000 data dots within one period. So very good resolution. You can vary the temperature, for example, in the contact from -45 up to 1000 centigrade, which gives you a wide range to cover with your applications and with your tests. And we have online signal processing within our electronics, so that you can always make sure that the signals are timely synchronously. So if you want to understand effects, you have to be sure that, for example, the displacement signal and the friction force signal come in the same microsecond. If you have a time offset in between, then you can't really interpret the results, because they are, you can't correlate them. And then, of course, you can export all the data to other file systems, which allows you to import your generated data directly into calculation softwares for your further simulations and so on. The test programming we will show you in the live demo. It's very easy and intuitive. You can do it on a touch screen with your fingers in a very simple way, so that you can prepare and set up the test parameters very simple. And they are stored to the PC, so you don't have to manipulate them each time. You can just relaunch the test by hitting only one button. I think Felix and Laura will demonstrate this later in the software. The parameters for the fretting standard method are displayed here. You can find them in literature as well and in the records of this webinar. And the materials which we are using for the test are, in this case now in the standard method and in the demo, a ball, steel ball on the right bottom against a steel disc, which is the second from the right in the lower line. And for applying the grease, we have a grease caliper which applies a well-defined amount of grease. And then we have the tension pieces and the sample holders. You will see how we install them into the test chamber. At this point, we could quickly run the first demo video. Can I launch it from here?
Yeah, I'll launch it now. So sample preparation.
Sample preparation, please.
Okay.
Yes.
Launching now.
So this is a little bit speed up, so don't be confused. You mount the ball into the ball holder. Of course, you have to clean the samples before in the ultrasonic cleaner with a cleaning solvent. Then you mount the ball in the ball holder. If you need lubricant, you will see that we apply it on the disc. In this case, we are applying grease with a spatula. There you always have to make sure that you don't include air bubbles when you apply the grease. Otherwise, they will falsify the results because the volume is not the same. We usually apply it into the grease caliper with a spatula. as I said, if you're running dry tests with coatings, for example, then of course you don't need a lubricant. You remove then the spatula and you mount everything into the test chamber. You need the clamping device, very simple. You put the disc on the oscillation block, the receiving block, and you mount it with one single screw very easily, but you don't tight it entirely at this moment. This will come later. Then you install the ball with the ball holder, also very simple with only one screw. You loosen the ball a little bit so that it falls down onto the contact, because later you apply a preload and then you tighten everything till the end.
I'll just bring the slides back up. There you go.
Great, thank you. And after the test, okay, here we can already run the second video, please.
Absolutely.
After the test, you uninstall then the samples, clean them with a wiper only. So you don't have to clean them in the ultrasonic cleaner, because sometimes you also have tribochemical layers on the surfaces, and we don't want to remove them, because we want to have them on the microscopic image so that we can judge after the test if there were reaction, which kind of reactions, and if the entire surface was coated, for example, during the test by those tribochemical reactions or not, or if we have clean metal to be seen on the microscopic image. And then, of course, you need a good microscope to take the picture of the wear scars. In our case, we are using a laser scanning microscope, which makes it very easy to measure the wear dimensions. On the one hand side, the diameter of the wear scar, for example, and on the other hand side, we can easily then evaluate the wear volume on the counterpiece, on the disc. And this gives you then, together with the COF, coefficient of friction, you have then three simple values which characterize the anti-fretting performance of your the test system, or of your samples. On the one hand side, we have the coefficient of friction at the test end, represented in red. Then we have the wear scar diameter and the wear volume on the disc. So three very simple values which describe the system. And as I mentioned already, with the industry standard of the SRV, we are set in many specifications. The newest one was now the HPM specification for high performance multi-purpose greases at the NLGI, and so we are also settled in many other specifications. So at this point, Sam, I would like to jump to the live demo. So did I understand correctly that we have 15 minutes to go?
Yes. Well, if we go
Okay.
to, well, it's about 20. So we do that.
Okay.
Yeah, about 15 minutes, and then 5 minutes for questions. Another quick note: I've just released another poll question. Just if anyone from the audience would like to receive further information from Optimol, please go ahead and answer that question. I will pass your emails on to them. So yes, Felix and Laura, if you could please come on stage. I'll stop.
Yes.
Stop sharing that. Okay.
So now, as you can see, the specimen are already prepared and maintained, and now we start together a test run. It's now the test run for the EP test, which means we are determining the highest load which the lubricant is working with. And Gregor, can you share the screen for the SRV?
Yes, sorry. This is number 402.
You are seeing the load is now applicated. Nicht on stage. Nicht auf stage. And here on the screen you see the preparing for the start condition, and we have the 50 degrees and also the 50 Newton on this test method. And after that, to guarantee the same temperature level in the whole test chamber, there is a start delay. But for the demo, we can skip that. And then the test is running. Maybe you can hear it or also see it, but the stroke is very small. And here you see your values you want to drive and the values that are driven and measured by the system. And for making a test run, you're very flexible. First of all, you need to set up a set point profile. You go there and loading it, and you decide for oscillation or rotation. We take oscillation.
This is what Felix demonstrated
now. We can give that here a name. And here we can set up all the hardware tools that are set up. And like a high temperature block or which load cassette we used. And for different ranges of load we want to run, there are different load cassettes available. And for the settings, we can use some cutoff values. Means if the cough, for example, is over the 0.3, like here, for over 20 seconds, then the system is stopping automatically. And you can also do that for other kind of values like the stroke cutoff and so on. And you can also put an resistant measurement, and then you have one more cutoff value to set up. Then in the setup profile, you set up the parameters like the test temperature at the beginning, or the test load, the stroke, the frequency. And we are also able to to make some steps during the test run, and it looks like that. If we want to set it up, then we can decide how long the step needs, and if it's linear changing or doing it by a step. And we can do it very creatively, like, and then we go backwards to 50 and 20. It's very easy to use, and we can do that not just for the test load, also for the stroke or the frequency we want to drive. And yes, that's for the set point profile. We also need a data logger where we set up what values we want to measure. For that, we go to the data logger, and normally there are some default data loggers also available, so you don't need to do a data logger for every new test run.
I'm sorry, Felix. Your microphone is not perfectly.
Yes.
Yeah.
Now
Now
okay.
It's perfect.
Thanks. And
Welcome.
here, creating a new data logger also for oscillation. Here we set up our hardware devices like the ATD measurement or the electrical resistance measurement. And if we set up what is available in the hardware, we can set up which data we want to sample, like the block temperature or the frequency, the test load, the cough sigma value. There are different values that are interesting. Yes, and the last step before we can run a test run is to put the setup profile and the data logger together into a starting procedure. Also oscillation. And here we can give it a name. Here is the process settings. They are close to always a default settings. Here we put a set point profile. We can search for the name we given before, or filter it by the date for today or yesterday, or so on. And also we need to add the data logger. And if we done that, we can run a test run. Like now a test run is running. And
you have to set up once, and then you can launch the test repeatedly with this starting procedure which you once created. So it's only one preparation for the entire test series. Sorry, Felix.
Exactly. And this is recommended for a big test matrix where you have the same method but different lubricants to test. And here on the searching button on the left side, you can look for some starting procedure you are programmed, and like the ASTM D.6. And here you can choose on the right side if you are looking for a starting procedure or a analysis, like a already run test run, or if you are looking for just a set point profile. Exactly. And so now here we could click on it and automatically start, but it's not working now because we are running a test already. So if we want to go to the live view, this is a big benefit of the SRV, that we can show the test run during it runs. Now we have here a little bit fail of the grease, and yes, that normally it should fail on 300 Newton, but it can happen that it show no. Okay, to look on the analysis, we have here an example of a test run where a lot of values are measured, like the red graph is the static coefficient of friction. The dark brown graph is the dynamic coefficient of friction. Blue is the stroke here in that case. Purple is the load that are run in steps. And you can easily add some data you are tracked here. You can give it a axis on the right or left side, which you want. And here we have also the orange or golden graph. It's the resistance measurement, where we can measure the micro context of the tribology system. Exactly. On the other stage, on the other machine, on that machine, there is the anti-wear test method running. You can see close to nothing because the stroke is very small. And if you want to see the live view of it, this is a bigger, better grease. It don't have any frettings happen till now. And this test is running for 4 hours. And after that, we are measure the scar, the wear scar of the ball and of the disc, and then we evaluate if fretting happens or not, or we are determining the wear rate of the grease.
I have to interrupt you shortly. For those who are more interested in the scientific or science of tribology, you can see, for example, in the chart that we don't not only record the one COF, but indeed you have the coefficient of friction, the static coefficient of friction, which means zero sliding speed at the turning point. This is the light red graph. And then we have the effective coefficient of friction, which emphasizes the sliding period, the sliding regime, which is the dark red line. So you have immediately within one test a feedback about the static and the dynamic frictional performance of the system. Sorry, Felix, go ahead.
And also to share at last the HRA graph, we need to switch the machines again. Sorry for that. Exactly. Here the same test run like before, and we are looking now at the HAR graph. As you can see it here. Here in the blue we have the stroke scene where we change between 0.03 and we are measured with a high definition the coefficient of friction. And as you can see here where the moving the velocity sign is changing on the highest point of the scene graph, we are changing the coefficient, and there we have the highest peak. This is the static coefficient, and on the whole test run, the effective value of that graph is represented the dynamic coefficient of friction. That's it for the demonstration. Hopefully you received any information. And if you have any question, I'm glad to ask.
Yes, thank you, Felix and Laura. Very good demonstration. So, Sam, you are taking over now.
Yes, I will. So I'll just resume. So we had a few questions and comments on there. So the first one's quickly about the with regards to the question from Marlon about Let me oops. Yep, sorry. So with regards to the question about incubation during fretting, we had a comment from Ben Beek, who's with us. So Norbert Schwarzer used his SIO modeling software to study incubation in nanofretting. So you can follow pressure distribution evolution with changing depth in first cycles. So thanks for that, Ben. So there's Marlon paper to look up for that. So if you look at Norbert Schwarzer's papers. The question on how important is substrate fretting where if coatings are applied. Still very important. Depends on how hard wearing your coating is. But of course, substrate support for the coating is extremely important. So probably better for the replay so we don't go back, as I'm just conscious of time, so we keep going through questions. You can get wear through of the coating, of course, and then you will then have the substrate wearing. So yes, extremely important. I mean, it depends on, there's a lot of things to, relative hardnesses, relative elastic moduli, load support, type of substrate, type of coating, and so on. Just a quick comment as well. So for everyone who registered, the replay will be sent to you via email, and additionally, it will also be available on our website later today. Right, so I think we have a few more questions. So I'll just bring the Optimol website link there if anyone would like to do that. Gregor, would you like to come back on? I think we have some questions specifically related to the SRV now.
Yes, of course.
So we got one here. So someone is asking, is only ball on flat geometry possible? Can any other contact geometry work?
Yes. You saw in the presentation, you saw the holders, so they are very adaptive. There are also standard holders for other geometries. The standard geometries are ball, flat, line, and area, which means different ball sizes, different cylinders, crosswise, lengthwise, upright, so in every orientation, and also flat on flat.
Okay. Another question here from Maxim. Can your devices show the parts, not specimens, that need to be replaced when the device is feeling that they are worn or working improperly?
Can your devices show? So I think this is maybe targeting on component testing. So if you are really able to test entire components, and this is also possible, we also have adapters and mounting devices so that you can take out from the series production the components. Maybe you have to modify them slightly if they are big components, and then you can mount them easily into the test rig and do the tests online on your components.
Yeah, I guess I think the other thing with feeling worn, I guess that would be more relating back to the demo. If there's a specific set point for which you're going to say the coefficient of friction has reached that, then it has failed. You could probably say, I mean, this is Maxim, this is probably going to be specific to whatever your component is, whatever your application, but that's probably, it's something that, as we covered in the demo, is definable in the software. So there is that. Another question from Maxim as well on how close is it to Industry 4.0?
That's a very good question. So the software is entirely connectivity to on the one hand side to network, of course, and on the other hand side on I can't recall. It's an industry protocol for machine-to-machine communication, and the machine comes, or the software comes with this protocol, and you can simply connect it then to your smart factory or smart laboratory, and it will send out the data online to your control center in the network.
Okay. Question from Ben for you, Gregor. Is the precision in static and dynamic friction coefficient the same in the SRV, i.e., in the plot, is the dynamic averaged over more points?
Both are averaged only over one period of movement. So we don't like filtering so much because filtering is something you can do later. We want to show the raw signals. The repeatability or the precision of both are very good. You might know that within the standard processes, we are running international round-robin tests every year where we verify the precision, and the precision is in the range of the second or third digit after the point. So very good precision, and this is for both friction coefficients.
Okay, great. Another question here from Barrett. Is cylinder on cylinder, I presume he's asking, is it possible to have cylinder on cylinder contact geometry for fretting
Yes.
layer?
Simply and shortly, yes.
Yes. And then I think we will have this will be our final question here. If temperature sensors, friction force sensors goes bad, does it indicate that they require replacement?
Yes, it does. We have reference runs which the user has to run every 4 to 6 weeks, and as soon as you see any deviation to the reference behavior, you know that something is not okay. And on the other hand side, the electronic can also detect failures of the system, which are really very rare.
Okay. Excellent. So thank you for your questions, everyone, and thank you all for joining today. So just quickly do that. If any of you would like to look at any of our past Surface Ventures events, and also to register for our next one on the 30th of September, that registration link is available on our website. I would like to thank Optimol and Gregor, the rest of the team. Thank you very much for running this demonstration today. It has been fantastic. Thank you.
Yes, thank you, Sam and Thomas, for hosting this event. It was a great pleasure for us to participate, and we learned a lot. Thank you.
Yes, some great questions. So brilliant. And with that, I will bring this session to a close. So thank you very much. And thank you everyone that attended. Okay. Bye.